Welcome back to part 2 of thermodynamics practice question. First question is 10 kilowatt of heat is to be removed from cold source at 20 degrees Celsius and rejected to ambient at 30 degrees Celsius. We have to find work net and COP. So this is a refrigeration based question. We have our heat sink at 30 degrees Celsius and heat source at 20 degrees Celsius and 10 kilowatt of our heat transfer is taking place and some work is given provided, so we have to calculate this work net. So we know that our COP of refrigeration is Q out by W net, which is Q out by Q in minus Q out equal to T out upon T in minus T out. So using these two equations, this one and this one, equating these, Q out by W net is equal to T out by T in minus T out. We know our Q out is 10. Work net we have to calculate, and temperature out is 253, which is 20 degree plus 273 Kelvin in terms of Kelvin, and upon T in, which is 30 plus 273, which is 303 Kelvin minus 253. So work net comes out to be 1.97. Next question is for heat pump, cold system at 0 degrees Celsius and hot system is at 60 degrees Celsius. Heat rejected at 8000 kilojoule per hour. We have to find minimum electric power consumption. So using the question, we have drawn diagram. So this is our hot system at 60 degrees Celsius, which is 333 Kelvin, cold system at 0 degrees Celsius, and some work or power is being provided. Q1 and Q2 is given as, heat rejected is given as 8000 kilojoule per hour. So COP for heat pump we know is temperature of high hot side, yani means TH by TH minus TL. So TH we know is 333 and TL we know is 273. So COP comes out to be 5.55. And COP for heat pump is also equal to Q2 by W. Q2 being rejected heat and W is work or power. So our work we have to calculate, COP we have calculated, Q2 we know, we can from there we can calculate power is equal to 0.4 kilowatt. Next question is based on heat transformer. So we are given two sources at 400 Kelvin, 300 Kelvin, and heat transformer at 350 Kelvin is supplying 100 kilojoule of heat, and it is going into Q1. Q1 heat is going into 400 Kelvin source and Q2 in 300 Kelvin source. We have to find Q1 and Q2. So from balancing we get that Q would be equal to Q1 plus Q2. So Q1 plus Q2 would be equal to 100. And from Gauss's inequality we know that Q by T is equal to 0 for summation for all the processes going in the system. So Q by T for heat transformer minus Q1 by T1 upon Q2 by T2 would be equal to 0. So it would be 100 by 350 minus Q1 by 400 minus Q2 by 300 would be equal to 0. Now we have two equations. From this we can calculate Q1 and Q2. Next question is reversible engine is given. 3 thermal reservoirs are there and deliver at 50 Kelvin. Power is delivered from all the 3 reservoirs. Engine absorb at 1000 kilojoule per second from reservoirs at 600 Kelvin, and heat rejected to reservoir having temperature 400 and 600 Kelvin we have to calculate. So basically they are saying is we have 3 reservoirs at 600, 400 and 300 Kelvin, and they are acting as a engine and they deliver 50 kilowatt of power or work, and heat which is being absorbed from 600 Kelvin source is 1000 kilojoule per second. So we have to calculate heat rejected to reservoir Q2 and Q3. What is heat being rejected to Q2 and Q3 at temperature 400 Kelvin and 300 Kelvin reservoirs? So thermal efficiency we know is work by Q total, which is heat supplied. And from balancing our heat, we know that 1000 kilojoule per second heat is being supplied, and Q2 and Q3 is and work is going out of the system. Q2, Q3 and this work is going out of the system. So 1000 would be equal to Q2 plus Q3 plus work. So Q2 plus Q3 would be equal to 950. And from Clausius inequality, we know that 1000, this is going into the system. So 1000 by 600 minus Q2 by 400 minus Q3 by 300 would be equal to 0. So using both the equations, we get our Q3 as minus 850 and Q2 as 1800. By minus, with the sign of this minus, we know that Q3 is not going out of the system, Q3 is going into the engine. Next question is, reversible heat engine extract heat from high temperature source at rate of 100 kilowatt and reject heat to a sink at rate of 50 kilowatt. Work from heat engine drive reversible heat pump operating between 290 Kelvin and 348 Kelvin reservoir. We have to find rate in kilowatt at which heat pump deliver heat to high temperature reservoir. So basically we have a heat pump, heat engine and a heat pump, and heat engine is operating between some temperature, and then it is supplying 100 kilowatt of heat is rejected from high source to low source, and 50 kilowatt heat reaches to the low temperature sink. So heat engine supplies some work to heat pump. So the work supplied would be 100 minus 50. Work which heat engine is supplying to heat pump would be 50, and heat pump is operating between 348 Kelvin and 290 Kelvin. We have to find what is the amount of heat, rate of heat is being supplied to 348 Kelvin reservoir. So we know that COP of heat pump is temperature of high temperature source TH by TH minus TL. TH is for high temperature, TL is for low temperature. So COP comes out to be 6.7. We know that for heat pump, high temperature is given as 348 and low temperature is 290. So it would be 348 minus 290. COP comes out to be 6.7, and COP also equal to Q by W. So in heat pump, we know W is given, W we have calculated from heat engine work which is coming out, which is 50, and COP we have calculated 6.7. So putting the values in here, we can calculate our Q, which is equal to 300 kilowatt. Next question is, reversed Carnot cycle refrigeration maintain temperature of minus 5 degrees Celsius. Ambient air is at 35 degrees Celsius, and heat gained by refrigerator at constant rate is 2.5 kilojoule per second. We have to find power in watt required to pump this heat out continuously. So our high temperature reservoir is at 300 Kelvin, which is 35 degrees Celsius, and low temperature reservoir is at 268 Kelvin, which is minus 5 degrees Celsius. And we have to find our work W, power required for the pump to continuously work, and our constant heat rate is given us, which is a heat rate going from low temperature source to high temperature source is 2.5 kilojoule per second. So we know that COP for refrigeration, it is mentioned in question, it is refrigeration process. So COP for refrigeration is low temperature upon high temperature minus low temperature. So COP comes out to be 6.7. And we also know that COP is equal to Q by W. So putting in the values of COP 6.7, Q 2.5, W we have to calculate, and we are multiplying it with 1000 to convert kilojoule per second into kilowatt. Sorry, kilojoule per second is equal to kilowatt, and 1 kilowatt is equal to 1000 watt. So we are multiplying it by 1000. So our work, which is equal to power, comes out to be 373.13 watt. Next question is Carnot engine. CE works between A and B. TA is given as 900 Kelvin, TB 500 Kelvin. Carnot engine 2 works between B and C, and temperature of C is given as 300 Kelvin. Heat rejected by Carnot engine 1 to reservoir B is used by Carnot engine 2. From one cycle of operation, A absorbs Q is equal to 270 kilojoule. We have to find net heat rejected to reservoir C by Carnot engine 2. So reservoir A, it has 900 Kelvin, B at 500 Kelvin, C at 300 Kelvin. QA is given to us as 150 kilojoule. Sorry, in the question QA was 150 kilojoule, and QB we have to find, and QC we have to find. So in our Carnot engine 1, efficiency we know is equal to 1 minus TL by TH, and it is equal to 1 minus QL by QH. So in engine 1, we know temperature of low temperature reservoir 500 Kelvin and high temperature reservoir 900 Kelvin, and QA, which is heat transfer rate from high temperature reservoir, which is 150, and QB we have to find, and it comes out to be 83.33. Now we would apply the same formula on our Carnot engine 2. So for Carnot engine 2, efficiency 1 minus TL by TH is equal to 1 minus QL by QH. Low temperature reservoir is at 300 Kelvin, high temperature 500 Kelvin, equal to low temperature reservoir QC we have to calculate, and QH we have calculated as high temperature reservoir, which is QH is equal to QB we have calculated as 83.33. Now solving it, we get our QC, which is low temperature reservoir for this C reservoir, we get 49.99 kilojoule. Next question, heat engine is there, and two reservoirs are present at 400 Kelvin, 370 Kelvin. Heat from first is 40 kilojoule and second is 37 kilojoule, and we have to find Q, which is being supplied to 320 Kelvin. Both of these are combining heat, are coming to heat engine, and then so we have to calculate from Clausius inequality Q by T is equal to 0 for the process. Then so these, the incoming into heat engine would be equal to the outgoing. So it would be Q, which is, let's name it 1, 2, and the final which is going out to be 3. So 1 plus 2 would be equal to 3. So Q1, which is 40 by T1, which is 400 Kelvin, plus Q2 37 kilojoule by T2 370 Kelvin would be equal to Q, which we have to calculate, upon T3 320 Kelvin. So Q comes out to be 64 kilojoule. Next question is, heat pump absorbs 40 kilowatt heat from outside at 250 Kelvin, while 10 kilojoule of work is supplied to it. It delivers heat to room at 300 Kelvin. So we have to find COP of heat pump. So in this question, we have 250 heat pump is there, 250 Kelvin low temperature heat sink, sorry, low temperature reservoir, and 300 Kelvin is high temperature reservoir. And the work which is being done but is 10 kilowatt, and Q which is going from 250 Kelvin is 10 kilowatt of heat Q. So total Q which is coming to 300 Kelvin reservoir would be this Q plus this Q coming from this part from low temperature reservoir and this one. So adding this we get our total Q for 300 Kelvin reservoir, which is 10 plus 10 comes out to be 20. So COP is Q by W. So Q is 20 kilowatt and work which is being provided to heat pump is 10. So COP would be 20 by 10, which is 2.